Hello, everyone, and welcome to Kognito Key. I am absolutely thrilled to have you here today. Now, have you ever stopped to wonder how the purely digital brain of a computer manages to actually control the very physical, analog world around us? It's kind of wild when you think about it. Well, today, we're going to explore the ultimate bridge builder in electronics, the digital to analog converter, or DAC for short. Okay, let's dive right into this explainer.
Here is a quick look at our agenda. 1. Bridging digital and analog. 2. How DACs actually work. 3. Taking a look inside the DAC 800. And 4. Interfacing it with the 8085 microprocessor. Section 1. Bridging digital and analog, from ones and zeros to the real world. So, what exactly is a DAC? Simply put, a digital-to-analog converter is a device that translates digital signals straight from a microprocessor into an equivalent analog form. But here's the really fascinating part, and it's absolutely crucial: the reference value. You see, a DAC can't just magically guess how big an output should be. It absolutely requires a reference analog voltage or current to base its conversion on. Without this baseline reference point, that binary data literally has no physical scale to translate into. This brilliantly illustrates the core communication problem we face in electronics. On one hand, we've got the microprocessor. It's incredibly smart, right? But it only speaks in binary ones and zeros. On the other hand, real-world applications, things like spinning motors, sounding alarms, or heating elements, they simply don't understand binary. They need continuous, smooth, analog signals, like varying voltages or currents, to actually do their job. The DAC is our necessary translator. Okay, Section 2. How DACs actually work, under the hood of the converter. First up, we really need to understand the concept of resolution. Let's say we're using an 8-bit DAC. That means our input is an 8-bit binary value. And since 2 to the power of 8 is exactly 256, our DAC can provide 256 distinct, separate analog steps based on our starting reference voltage. Think of it like a giant staircase. Every single analog output generated is going to be a specific, exact multiple of this baseline resolution step. Now, broadly speaking, we can classify DACs into 3 main categories based on what they produce. We have current output DACs, voltage output DACs, and multiplying type DACs. While the first 2 just describe the physical nature of the output signal, fundamentally, almost all of them function as multiplying DACs. Why is that? Well, because the final analog output is always the mathematical product of the applied digital input multiplied by that all-important reference value we talked about. Let's see how this physical architecture actually comes together inside the chip. Typically, a DAC relies on what we call an R/2R resistive ladder network. Step 1. Switching transistors take your binary input and connect the internal resistors to either the ground or the reference voltage. Step 2. This highly precise resistor network combines the resulting currents in strict binary proportion. And finally, Step 3. An operational amplifier, or op-amp, takes this mathematically perfect proportional current and converts it into the final, usable output voltage. It is just brilliant circuit design, don't you think? Moving right along to Section 3. Inside the DAC 0800, exploring a classic 8-bit converter. Let's quickly run through the specs of this 16-pin chip. It features an 8-bit resolution and provides a current output, specifically generating an I-out and its complement, I-out. But the absolute standout feature here is its speed. It boasts a lightning-fast conversion time of around 100 nanoseconds. On top of that, it accepts a highly flexible supply voltage, ranging anywhere from plus or minus 5 volts all the way up to plus or minus 18 volts, which makes it incredibly easy to use with standard logic families. And finally, Section 4. Interfacing with the 8085 microprocessor, wiring the system together. When we go to connect our super fast DAC 8800 to an 8085 microprocessor, we run into a fundamental timing hurdle. Even though 100 nanoseconds is fast, the conversion still takes a definite amount of physical time. Because of this, the digital data has to be held continuously stable at the DAC's input. Now, the microprocessor is way too busy to just wait around holding data, so we introduce a middleman, an 8-bit latch, like the 74LS273. This component acts as a secure holding area for our data. Let's break down the exact timing sequence for this interface. Step 1, the 8085 processor securely loads the digital data onto the 74LS273 latch, triggered by chip select signals. Step 2, the latch completely takes over, holding that data perfectly steady. Step 3, the DAC processes the stable input, taking its required time to generate the accurate analog output. And Step 4, only after that conversion is totally complete does the system load the next piece of successive data. It's a wonderfully synchronized routine. And that leaves us with this final, powerful thought. By mastering the DAC interface, We give the digital mind of a microprocessor the ability to control the analog actions of the physical world. Thank you so much for joining me today on Kognito Key. I really hope this explainer has helped you grasp these essential concepts. If you found this explainer helpful, please hit that subscribe button to join our Kognito Key family, and definitely like and share this explainer with your peers. So, I leave you with this question. Now that you know how to build the bridge, what kind of analog world will you command with your digital designs? Keep learning, keep building, and I will see you in the next one.